Have you ever wondered how a computer learns to play a game like chess or Go? I mean, really master it without someone programming in every single move? Well, you've landed in the right spot. That's the magic of reinforcement learning. And if you got this on your exam syllabus, stick around, because we're going to break down the key concepts you absolutely need to know. Let's dive in.
Okay, so here's the plan. First, we're going to tackle why reinforcement learning is even a thing. Then we'll get into its core framework, the real nuts and bolts. After that, we'll unpack the difference between two super important ideas, rewards versus values. Then we'll see it all in action with a classic algorithm and a pretty mind-blowing world champion example. And of course, we'll wrap everything up with a quick summary that's perfect for your exam prep. So first up, why reinforcement learning? What's the big deal? Well, a lot of machine learning is about learning from a big pile of data you've already collected. But RL is different. It's all about learning by doing. It's built for those tricky problems where you have to figure things out as you go by actually trying stuff in the world. And that brings us to the central puzzle of reinforcement learning. I mean, think about it. In a super complex game, you can't possibly write a rule book for every single situation, right? There's just no way. So the big question is, how can a machine learn to make smart choices all by itself?
Well, the secret sauce is all in the kind of feedback it gets. See, with supervised learning, the feedback is instructive. It's like having a teacher who just tells you, nope, the correct answer is 4. But in reinforcement learning, the feedback is evaluative. This is more like a coach shouting from the sidelines, hey, nice shot, or oof, that was a bad move. The coach tells you how good your action was, but, and this is the key part, they don't tell you what you should have done instead. You have to figure that out yourself. And that whole process of trial and error, that's the absolute core of RL.
Okay, so to make sense of this whole learning process, we need a model. And luckily, it's a really simple but super powerful one called the Agent Environment Framework. Seriously, this is the bedrock of pretty much any RL problem, so let's take a look at the pieces. First up, we've got the agent. This is our learner, our decision maker. Think of it as a robot learning to walk or the AI playing chess. Its entire job is to look at the world and then decide what to do next. Simple as that. And where does the agent live? Well, it operates inside an environment. The environment is basically everything else. Everything the agent interacts with but doesn't have complete control over. For a chess AI, the environment is the board, the pieces, and the other player. And here's a tip for your exam. The line between the agent and the environment is all about control. The agent can't just decide to change the rules of chess, right? That's the environment's job. So how do they interact? It's a constant loop, a back and forth. First, the agent looks at the current situation. We call that the state. Where are all the chess pieces right now? Then, based on that state, it chooses an action. It moves a piece. The environment sees that action and does two things. It gives back a numerical reward, like +1 for winning, -1 for losing, and it presents a new state. And then the whole thing just repeats. State, action, reward, new state, over and over. That's the engine of reinforcement learning. All right, so the agent gets these rewards, but just chasing the biggest immediate reward, well, that's a terrible strategy. It's like only ever eating candy because it tastes good right now, even though you know a healthy meal is better in the long run. To be smart, the agent needs something more. And this leads us to one of the most important distinctions in all of RL, the difference between rewards and values. Okay, so a reward is that immediate hit. It's the points you get right after making a move. A value, though, that's the long game. It's a prediction of all the rewards you're likely to get from this point forward. Think about it. Sacrificing a pawn in chess gives you a negative immediate reward, right? You lost a piece. But if that move leads to checkmate in 10 moves, its value is incredibly high. The real goal isn't to get the next reward. It's to be in situations with the highest long-term value. Yeah, I really like this way of thinking about it. Rewards are kind of like pleasure and pain. They're immediate feelings. But values are more like a wise, far-sighted judgment about what's truly good for you in the long run. An agent that just chases rewards is impulsive. An agent that maximizes value? Now that's a real strategist. So how do we capture this far-sighted judgment in code? We use something called a value function. And really, for a lot of RL algorithms, the entire game is just about learning a really, really good value function. Because if you think about it, if your agent knew the true long-term value of every possible position on the board, choosing a move would be easy, right? You just pick the move that leads to the position with the highest value. Okay, so the goal is to learn this value function. But how? How does an agent actually figure that out from scratch? Well, Let's look at a classic algorithm that shows us exactly how this can be done. It's called SARSA. SARSA is a type of algorithm called temporal difference learning, or TD learning for short. And the main idea here is brilliant. You don't have to wait until the very end of a game to update your strategy. Instead, you learn from the difference between your guess now and your guess one step in the future. It's like your GPS doesn't wait till you're totally lost to reroute. It adjusts your ETA after every turn based on new information. That process, updating an old guess with a new guess, is called bootstrapping, and it's what makes these algorithms so fast and efficient.
And here's how it works. The name SARSA is actually an acronym for the 5 pieces of information it uses. You're in a state, you take an action, you get a reward, you land in a new state, and then, and this is the key part for SARSA, you choose your next action. SARSA. See? It uses that next action to update its value for the first action. This is what makes it an on-policy algorithm. It learns based on the actions it's actually taking, not some hypothetical best action. It learns from its own experience, good and bad.
Okay, that's the theory. But does this stuff actually work in the real world? Oh yeah, big time. Let's check out one of the most famous and honestly groundbreaking examples of these ideas in action. Meet TD Gammon. This thing is a legend in the world of AI. It used that exact same TD learning idea we just talked about and paired it with a neural network to estimate the value function. But here's the absolutely wild part. They gave it almost zero human knowledge about how to play backgammon. None of the standard openings, none of the strategy. It just played millions of games against itself, learning from scratch. And the result? It got so good, it could play against the best human grandmasters in the world. This was a huge deal. It proved that an AI could reach world-class levels just by learning on its own.
All right, let's bring it all home with a quick review. If you've got an exam coming up, these are the key takeaways you'll want to have locked and loaded. Okay, let's run through the list. First, remember, the feedback is evaluative. Good move or bad move, not instructive. Do this instead. Second, the goal is to maximize the cumulative long-term reward, not just the next little prize. That's what the value function is for. Third, the whole system is built on that agent environment loop. State, action, reward. Fourth, algorithms like TD learning let the agent learn on the fly by bootstrapping from its own estimates. And finally, don't forget the big dilemma: exploration versus exploitation. Do I try something new and risky, or do I stick with what I know works? Getting that balance right is everything. And that's a crash course in the core features of reinforcement learning. So I'll just leave you with this to chew on. Now that you've got the basics down, what other crazy, complex problems could be solved by an agent that learns just by trying things out? We're talking about everything from managing city traffic to discovering new drugs. The possibilities are pretty amazing. Anyway, I hope this helps. Good luck on your exams.